Okay, welcome everyone. So I've started the session and I'll wait for 2 minutes so that people can join the meeting. It's already 3. So let me wait for some time so that if someone wants to join the interaction, they can join. Otherwise, I'll upload this video on YouTube and you can watch later. Okay, it's already 3:05 and nobody has joined yet. So I guess I'll start the session and you can always join in the middle of the class. That is fine. and whatever part you have left, you can watch it on YouTube. So I'll start with the first question then. Okay, so this is the question to start with. So what are we given? We are given a typical television picture tube. So we have a typical television picture tube, and there is an accelerating potential which is given to be 6.2 kilovolts. Okay. So we have accelerating potential. Let us write that as V accelerating, that is given to be 6.2 kilovolts. Okay, and what we want to find is the minimum value of wavelength of the continuous X-rays produced when the electrons strike the inner surface of the tube. Okay, so let's say we have a tube like this, fine, and then we have an accelerating potential applied here. Okay, so let's say this is V minus, this is V plus, and the potential difference delta V, that is V acceleration, which is nothing but 6.2 kilovolts. So the electrons, okay, so the electrons will be accelerated towards the positive potential, right? Like this, and they will hit the screen here, and this will lead to production of X-rays. So we will get X-rays. Okay. And now minimum lambda, which is the minimum wavelength of X-rays that we will require, that will correspond to highest energy, right? So highest energy. And what is the highest possible energy that we have here? This is nothing but E times V acceleration, correct? And we can, in terms of photons energy, this will be h nu. So h nu will equal to E times V acceleration. And now we know that our lambda is given by C by nu, right? So from 1 and 2, what we can write is, from 1 and 2, lambda will be this, right? And now we know all the values. So the value of Hc in electron volts, angstroms, this is given by 12400 eV angstroms. Okay. Therefore, we can write lambda to be 12400 divided by 6.2 into 10 to the power 3 angstroms. Okay. So this will simply give us 2 angstroms, right? Because this will become 6.2 thousand, and this is already 12.4 thousand, right? So this will just cancel out, and this will give you 2. So the correct answer will be option A. Okay. So is this question clear? Uh, do you have any doubts in this one for the person who is in the live session? If it is clear, then I guess we can move on to the next problem. And if you have any doubts, feel free to unmute yourself, ask the doubts, or you can even type your doubts in the chat box. Yes. You're not audible. Can you try speaking again? I couldn't hear you. Or you can even write in the chat box whatever you wanted to say. Your voice was not coming. Maybe you can try again.
Excuse me, sir.
Yeah, yeah.
Sanjeev Kumar, sir.
Yes.
It's understood, sir. It's easy
Yeah,
explanation.
yeah. Okay. Thank you.
Thank you, sir. Thank you, sir.
Okay, let me write the next one.
Okay, sir.
So we are given two electrons, with orbital angular momentum, orbital angular momentum L1 with L1 is equals to 1 and L2 with L2 is equals to 2. Okay, and then we are asked uh, what are the possible values of quantum numbers? What are possible quantum numbers for total angular momentum, which is capital L? Okay, and the options that are given to us is 3, 1 and 2, 1, 2 and 3, 0, 1 and 2. Okay, so this one is not as trivial as the last one, right? Here you have two electrons, and we are given that the angular momentum of first electron. So first electron, the angular momentum is L1, right? And the quantum number is given to be 1. Similarly, for second electron, we are given that the angular momentum is L2 and the quantum number is given to be 2. Now, how do you define the total angular momentum? So this was discussed in the class as the vector addition rule, right? So if you have two angular momenta, L1 and L2, then your total angular momentum, that will be L1 plus L2. Correct? This is what was discussed in the class, right? And now if we want to find the quantum numbers associated with L, what is the rule? Do you know?
Right. That's it. We place expensive.
Sorry, can you repeat?
The rule I forgot, sir. We place expensive.
Okay, okay. So the rule is very simple, right? So like how we are
Yes, sir.
given the quantum numbers for the individual ones, now what we want to do is we want to find the quantum numbers for the total angular momentum.
Okay, sir.
Now the rule is that these quantum numbers will go from the highest possible value to the lowest
Okay,
possible
sir.
value. So highest possible value will be L1 plus L2, right?
Okay, sir.
The magnitude, and the lowest will be L1 minus L2 and the magnitude. So this is 3 and this is 1, correct? Their sum is
Okay,
3 and their difference is 1. So that then the all the possible values, right? We are asked possible quantum numbers. So this will be starting from 3, then we subtract 1 all the way up to 1. 3 to 1. So this will be our correct answer. Okay. Is it clear?
Yes. Clear, sir. Clear, sir.
Okay. Thank you.
Thank you. Thank you, sir.
Okay. So then if this is clear, let's solve the next one. So this requires the magnitude of uh, this orbital angular momentum with L is equals to 3. Okay, so we are given the quantum number, that is L is 3, and now we are asked what is the magnitude, and these are your options. So yeah, do you know when you are given the quantum number L, how do you write the magnitude of orbital angular momentum? So we generally denote this by capital L, right? So this is our orbital angular momentum, and its magnitude will be this. Now, how do you write it in terms of small l, which is the quantum number L? How do you write it in terms of that? Do you know? Yes? No? Anyone?
Sir, we again write it for um, that L L is square times is comes here.
Yeah, the square root comes here.
Mm.
It is something like this,
Yes, sir.
right? And then you have h cut. So here you have L times L plus 1.
Yes, sir.
Correct?
Correct, sir.
Yeah. So here we are given the value of L already, right? So this small l here is 3. So then it becomes very straightforward to solve. We'll just put 3 and 3 plus 1 h cut,
Yes, sir.
and this 3 plus 1 is 4, and square root of 4 is 2. So let me bring that outside, and h bar we can write in terms of, so the answer is asked, you can see the answer is asked in terms of h, and here we have h bar, right?
Right, sir.
So what is h bar? It is simply h
Lambda
over,
by 2, lambda by
no,
2
no, no,
is
in terms of h, so it is h over 2 pi, correct?
yes. Right, sir.
Yeah, so this 2 will cancel,
Right, sir.
and then the answer will be
2, 3
h
by
times
2,
root
3
3
by
and divide by pi, right? This option C,
3. Right, sir.
correct?
Right, sir.
Okay. So this was discussed in the class, right? Whenever you have angular momentum and whenever we want to describe it quantum mechanically, its values are quantized. It is called space quantization, right? It cannot take any direction, but the direction, the theta values, they are fixed. Do you remember this? No? So let's say this is our z direction. This is the
Okay.
direction in which we apply the magnetic field. Okay, let us assume. And then what we do is we draw a semicircle like this. Okay. And then this our angular momentum, it can only, depending on this L, what will be the values of ml that we will have. Ml goes from minus L to L, right? So it will be minus 3, minus 2, minus 1, 0, 1, 2, 3. So total 7 values, right? So on this semicircle, we will have all these 7 values: 1, 2, 3, 4, 5, 6, 7. Okay. And then we can draw our angular momentum vector like this. Okay. Note that these are the only possible directions in which your angular momentum can point. Right. So it cannot point in any other direction. And the magnitude of the angular momentum is what we calculated here. So that will be the radius of the circle, right? The radius of the semicircle. That is the magnitude, and that is given by this equation right here.
Okay.
This is what we have calculated. Okay.
Okay.
Okay. So let's move on to the next one. So now we are asked potential energy of a magnetic moment, which is given by mu, in a magnetic field, which is given by B. Okay. So this becomes minimum. This becomes minimum when the angle between mu and B. So you have an angle between mu and B is, so basically they are asking what should be the angle between your moment and the magnetic field. So your options are 0, 60, 90, and 180. Do you know the answer to this one? That at what angle is your potential energy minimum?
90 degrees, sir.
No. Okay, let me draw a diagram. Suppose this is the direction of our magnetic field, like this. Okay,
Okay.
let me draw the field lines. And now you put a magnetic dipole. Let's say this is our dipole. I just put it in some random direction. Okay, and let's say it is making some angle theta. Okay, so I have chosen some arbitrary direction. I have put my magnetic moment here. Now, because of the magnetic field, now what is a magnetic moment? It is like a bar magnet. Okay, you can think in terms of small bar magnet. Okay, so you can think that there is a small bar magnet here, like this, right? Now, uh, when you keep it in a magnetic field, it will, what will it try to do? So you tell me, will it rotate in this direction, which is clockwise, or will it rotate in this direction? So you have kept your bar magnet here like this in a magnetic field, which is drawn by the white lines. What do you think will happen to this small magnet? Will it rotate clockwise or anti-clockwise? What do you think?
Couple of options.
Sorry?
couple action.
couple action.
Yes.
But in which direction? Will it, okay, will it try to go like this, or will it try to go like this? So this will be 90-degree, right? This will be 0-degree. What do you think? Will it go towards 90-degree or towards 0-degree?
Yes, sir. It's supposed to 0 degrees. Sir.
0-degree, right? Yeah. So it will try to align itself in the direction of magnetic field.
Yes, sir. Yes, sir.
Yes. And when it is trying to align itself in the direction of magnetic field, what it means that, so any system, it tries to go towards the lowest energy, right? So it will always go towards the lowest energy. So every system tries to reduce its energy. So if it is going towards 0-degree, that means the potential energy is minimum at 0 degrees,
Yes, sir.
right? So the answer will be A. Now there is also a formula for potential energy. What is that formula? Do you know? When you have mu and B, the potential energy U, that is given as minus mu dot B. Okay, so this is the formula for finding the energy of a moment.
Okay.
Now we can write the dot product. We can write it in terms of theta, and this will become the magnitude of mu, the magnitude of B, and
Okay.
cos theta.
Constant.
Yes, and minus sign. Minus sign is there, right?
Mhm.
So when uh, when our theta is 0, so cos theta will be
One.
1. Okay, so for theta is equals to 0, our u will then be minus mu b.
Nice.
And when theta is 90, our u will be 0, right?
Zero. Yes, sir.
And when theta is 180, cos theta will be minus 1.
Minus one.
So this will
Minus
become
one.
plus,
Plus one.
so mu
Plus.
b. Now which is minimum out of all these three? This is minimum, right? Because this is negative. Mu
Ah,
and b are the magnitudes, so they are positive numbers. And because this is minus, which means that your this potential energy is minimum and theta is 0 here. Okay? So
okay.
therefore answer is optional.
Yes, sir.
Clear?
Yes. Clear, sir. Clear.
So let's solve next one. So you are given chlorine, and the question is that the ground state of chlorine is 2p3 by 2. Okay. Do you recognize this notation? This was discussed in the class. Okay, what is mu b? Anyone? Do you know what is mu b? What does it mu b stand for? I'll write here.
It's magnetic moment.
Ah,
Moment.
it is the unit, and it is called Bohr's magneton, right?
No.
Bohr magneton.
No.
So its value is equal to, when you have hydrogen atom and you have electron in its ground state. So the magnetic moment corresponding to that, that is called as Bohr magneton, and it is a universal constant.
Yes.
Okay.
Mm.
Okay. Now before that, what is this notation? This is very important to solve this question. So we are given the ground state is 2p3 3 by 2. So to write the notation, the general formula is this. This is known as multiplicity, right? 2s plus 1, and here you give the value of L, and here you give the value of J. Okay, so you have all these orbitals, right? S orbital, p orbital, d orbital, f, and so on. So here we are given p orbital, right?
Yes.
So because we are given p orbital, what will be the value of L? Will it be 0, 1, 2? What will be the value of L for a p orbital?
It is 3 by 2.
No, no, no. L is the quantum number. L is the quantum number. So it's very simple. So you can just label them as this 0, 1, 2, 3, so on, right? And L is just this number. So L is 1 here. If it was s orbital, L will be 0. But because it is p orbital, L will be 1. If it were d orbital, L will be 2, and so on. Correct?
Okay.
Okay. Now, if you compare the superscripts, this one, you have 2 here and 2s plus 1 here. Now, you tell me what will be the value of s. So, if you compare here, you will get 2s plus 1, that is 2. Right? 2s plus 1 is 2. So, then your 2s is 1, and then your s will be 1 by 2. Correct?
Yes, yes.
So, I'll write 1 by 2 here. And j is already given to us. Okay? So, you can see this is 3 by 2 and this is j. So we can already write j as 3 by 2. Okay. So from this notation, we can very easily get all the values of L, S, and J just from this notation. Okay. Now what does the question ask? Question asks us to find the magnetic moment. Now how do you define magnetic moment? Okay. So this is also something which was discussed in the class, and you have a formula for this. Let me write the formula. So magnetic moment mu j, this is given by gj times mu b, which is Bohr magnetron, and under root j plus 1. Okay. Now we know j, it is 3 by 2. So let's put in j. So it will be gj mu b under root 3 by 2 multiplied by 3 by 2 plus 1. Okay. So what will be its value? Let me write here gj mu b. So this will be 3 by 2 multiplied by 5. Hmm. So this will be under root 15, right? Under root 15. And this 2 we can take outside the square root, right? Because this 2 times 2 is 4. And then gj, mu b. Now, we are almost done. We just now need to calculate the value of gj, right? Once we know the value of this g, so this is the Landé G factor. And Landé G factor is defined as, so this is defined as 1 plus j times j plus 1 minus L times L plus 1 plus S times S plus 1 divided by 2j j plus 1. Okay, we have already calculated all the values of L, S, and J. We'll just put in the values in this formula. Okay, so from here you
Okay.
can see L is 1, S is half, and J is 3 by 2. Okay, let's put in the values. So our G will become 1 plus 3 by 2 multiplied by 3 by 2 plus 1. L is 1 and S is half. 2 into 3 by 2 and 3 by 2 plus 1. Okay, this thing. So this will become 1 plus, and 3 by 2 plus 1 will become 5 by 2. So this will become 15 by 4 minus 1 plus 1 becomes 2 minus 2 plus this will become 3 by 2 multiplied by 1 by 2 will become 3 by 4.
Okay.
And then we divide this thing by, so this 2 will cancel out, correct? This 2 will cancel out. This will become 5 by 2 and this will become 15 by 2. Okay, so let me rewrite this 2 as 8 by 4. I can rewrite this 2 as 8 by 4. It will make our calculation easy. Okay, so 15 plus 3 is 18 minus 8 is 10. So 10 by 4, and 10 by 4 is nothing but 5 by 2. So this will become 1 plus 5 by 2 divided by 15 by 2. Again, these 2 will cancel, and this 5 will cancel with 15 to give you 1 by 3. So 1 plus 1 by 3, this becomes 4 by
Four.
3.
Okay.
Good. Now we have the value of G. We can put in this equation right here, which we have already calculated above. So if you put 4 by 3 there, our value of mu J, that will become root 15 by 2 into 4 by 3 mu B.
Yes.
Okay, so this 2 will cancel out here. And let's have a look at our options. Okay, so we have one option here. So this thing we can rewrite as, so if you see the options, there is options when you have under root over whole thing. So let us rewrite as under root 15, and this 2 will become 4 and 3 will become 9, like this, right? So cancel with 3, this will give you 5. So this will give you under root 20 by 3 times mu b, which is option C. Okay, just I've just taken this 2 by 3 inside the under root, so I've squared it. So 2 squared is 4, 3 squared is 9, so that I can write it in this way. Okay, any doubts in this one? This was
Okay. No doubt, sir. No.
okay. Okay, so no doubt. So yeah, let's solve next one. So in the class we were taught about uh, sodium lines, right? D1 and D2 sodium lines. So lambda of D1 sodium line 5890 angstroms, and lambda of D2 sodium line, that is given to be 5896 angstroms. Okay, calculate the effective magnetic field experienced by outer electron in sodium atom. Okay, and our options are 10.6 Tesla, 36.6 Tesla, 9.23 Tesla, 3.12 Tesla. Okay, so these are our options. Now, if you remember from the class, why do we get these two lines from sodium? This comes because of spin orbit coupling. So you have spin orbit coupling. So our spin of electron and the orbital motion of electron, both of them gets coupled. Okay, and that is known as spin orbit coupling. So when that happens, there is this transition 3p to 3s. Okay, and this gets splitted. Okay, this gets splitted because of spin orbit coupling. Okay, because what is the atomic number of sodium? What is the atomic number of sodium? Do you know?
No, sir.
Okay, so atomic number is 11. Now, if you want to fill the electrons, so the 1s orbital will have two electrons, right? Then 2s electrons will have two 2s orbital will have two electrons. Then 2p electron will have six electrons, correct? 2p orbital will have six electrons, and then finally your 3s will have one electron. Okay, so this is the outermost electron, this one, in which is in the 3s. Okay, so if you draw circles here, so if this is your nucleus, this is your n is equals to 1, so it will have two electrons, right? It will have two electrons, 1s2. Then the outer one, this will have eight electrons, right? So one, two, three, four, five, six, seven, eight. Okay, two will be in s orbital and six will be in p orbital. So this will be your n is equals to 2. Now your n is equals to 3 orbital. Okay? Let's say this is your n is equals to 3 orbital. It only has one electron, and this is the outermost electron, right? And this is what we are asked, right? Outer electron in sodium atom, right? So this is in, you can see this is in s orbital. So if you have this 3s, sorry, if you have this 3s, and here you have 3p, how many lines do you expect? We generally expect that there will be only one transition, right? But because of this spin orbit coupling, what happens that your 3s your 3s becomes s half, and your p orbital is split in two, like this. and one is called 2p half and other is called 2p 3 by 2. Okay, and now you have two transitions, therefore we will get two wavelengths, right? So we'll get two lines, and which are called D1 and D2 sodium lines. Their wavelength will be different. Okay, now we want to calculate the effective magnetic field experienced by outer electron. Fine, this is all good. So now let's try to find the magnetic field. So first of all, our frequency is given by c over lambda. And if you want to find the, so if you differentiate both sides, if you differentiate both sides, what you will get is delta mu, and differentiation of 1 over x gives you 1 over x squared, right? So this will become lambda squared and this will become delta lambda. Okay, so this is one relation where we have related that if you are given the difference in wavelengths, how do you convert it in the difference in frequencies? Okay, so this is the equation, because we will use it later. Why? Because the formula that we have is given in terms of delta nu. Okay, so our delta nu, this is the formula, eb by 4 pi m. Okay? So this is the formula,
Okay,
and
sir.
now this is equation 2. So using both 1 and 2, we can replace this delta mu by delta lambda, because in the question we are given delta lambda, right? You can see we are given wavelengths and we are not given frequencies. So we can replace delta mu by delta lambda. So the equation will
Sir,
become, sorry,
we write in difference.
difference.
Yes, sir.
Yeah. So this is what we will get. And now what we are
Okay.
asked to find in the question? Effective magnetic field.
How to?
Yes,
Okay. Yes, sir.
effective magnetic field. And what is magnetic field here? Magnetic field
That
is
is
B.
B.
Yeah. So what
Yes, sir.
this equation we can write in terms of B.
B is equal to
Yes. So this will become C over lambda squared,
C by W.
4 pi, sorry, 4 pi m by E multiplied by delta lambda.
Then,
Okay.
okay, sir.
Now we know everything, right? We know the wavelengths, we know the delta lambda. So this m is mass of electron.
No,
Right here. M is mass of electron and its value is 9.11, 10 to the
10
power minus 31 kg.
31.
Correct?
Yes.
And then this E is the charge on electron. This is 1.6 minus
1.6
9.
and then minus 11. Yes.
Correct?
Yes.
Coulombs. Okay. So we now just
Okay.
have to put in these values, and we already have the formula derived here. So let's just do that.
Okay, sir. C is equal
So C is speed of light. What is the value?
9 by 8.
Uh, This is the value. Okay. And now, what do we put for lambda? Okay. So if you see the question, we are given two wavelengths, right?
Yes, sir. By 8
So
minus
5890 and 5896. So we
6.
can put in any value. It won't change the answer by much. But what is better to use is take the average of these two. So this is 58 5890 and this is 5896. So the average will be 5893. Correct?
Okay.
So 90 and 96, average will be 93. So let's take that value. 5893 squared. Okay. And then this is simply 4 pi. M we have already defined 9.11. E we have also defined 1.6 10 to minus 19. And now what will be this delta lambda? So this is 96 and this is 90. So this will be 6 angstroms, right? So into 6. Now
26.
this was angstroms. So we should have written minus 10 here. Okay. So this will be the magnetic field. Okay. Now can you tell me what value are you getting? Okay, so here are the answers. Here are your options. Can you tell me which is the correct option? You can try to calculate the value. I'll give you 2 minutes. Okay. Did you get any answer?
No, sorry, sir. I'm doing some
Yeah,
mistakes in
it's
something.
yeah, you can do it. Yeah, it's little long. Take some time.
Excuse me, sir. My calculator is some mistakes. Some technical issues, sir.
Sorry.
Something my calculator is technical fault. So
Okay.
answers doesn't come correctly, sir.
Okay. Okay, let's do it together. Okay. So let's first take the powers to one side and the numbers to one side. So I'll multiply 3 with 4. So this will become 12 pi. And let's take this to be simply 9. Okay. Approximately. And in denominator, you'll have 5893 times 5893 multiplied by 1.6. This number. Right. And the powers will become, so this is 8 here, then minus 31 here, and then minus 10, Then this will become minus 20, so we can take it up, will become plus 20 and plus 19. Correct? Yeah. So this becomes minus 41, this becomes 39 and 8, 47. So 47, 41, so this becomes 10 to the power 6. I can write it as 10 to the power 6. Okay. Now let's take out our calculator and write these numbers. So this is 12 multiplied by pi multiplied by 9. So this is 339.3 divided by 5893 squared multiplied by 1.6. And this is 555,63918.4. Okay, and then if you divide this, so what do we get? We get there is also 110 to the power 6. So we get 0.0000366 into 10 to the power 6. Okay, so this just becomes 36.6 Tesla. That's it.
That's it.
Okay.
Sir, this is very simple method you are doing, sir.
Huh.
Yes, sir. Understood, sir. I think this is a very easy way to do this calculations.
Yeah, yeah.
Mm. Thank you, sir. Thank you, sir.
So do you have any doubts in this one?
No, sir. No, sir. It's, very clear, sir. Very clear. No worries, sir.
Uh, there was a lot of noise coming.
No doubt, sir. It's very clear, sir. Very
No.
easy way to showing this calculation. Very easy way and very easy methods.
Okay. Thank
I
you.
easily understand, sir. I easily understand, sir.
Okay. Thank you. So then let's do one more. So we have already done this one. One similar problem we have done. I want you to tell me. So if you have understood it or not. So if you have understood, tell me how to solve this. Okay.
Okay.
So we are given a magnetic moment. What is this noise coming from your side? There is some noise coming.
Yes.
Okay.
They are selling some vegetables and something,
Ah,
sir,
okay,
from
okay,
roadside.
okay. So you are given a orbital magnetic moment mu, right, of electron. Sorry, in hydrogen atom in s state. Okay, so this is in s orbital. Okay, and you are asked what is the magnitude of this moment, and your options are these: 0, 2 times mu b. What is mu b? We just discussed.
That is Bohr magnet.
Bohr magneton. right? This is more magnitude. Now these are your options. Okay, so you are given hydrogen atom and the electron is in S state, and you are asked to find magnetic moment mu. We have done a similar problem, right? So first you tell me that when an electron is in S state, what will be the value of quantum number L? What will be the value?
The state for zero, sir.
Zero. Very good. Zero. Okay. And now this is zero. And now how do you find out the magnetic moment mu? Okay. So I'll give you one hint. So if your L is the magnitude of your angular momentum, right? This is the magnitude of angular momentum. So your mu is
Yes, sir.
given as
By,
mu b by h cut times this. Okay.
sir.
So now you have to find out what is the value of this magnitude of angular momentum.
That is square root
This
of L,
this we
L into
this
L
we
plus 2.
this we did earlier, no?
Yes, sir.
One question.
Square,
What is how do you find this magnitude of angular momentum?
that is square root of L into L plus 1.
Correct. And multiplied by h cut,
Yes, sir.
right? So
Yes, sir.
this if we put
So,
the equation 2 in equation 1, we can write mu as mu b. This h cut will cancel, right?
yes, sir.
And this will become this. So this is the formula now. And what is the value of L?
L is 0, sir.
That is 0. So if
Mu
you
is
put 0
0.
here, mu will be,
Answer is 0.
yeah. So answer is A. Yeah, okay. Good, good. So this means you have understood, right?
Yes, sir.
Okay. So you can solve such problems. Good.
Yes, sir.
So this time I want you to solve it and give me the answer. Another very similar problem.
Yes, sir.
So what is the magnitude of orbital moment mu? Okay, again, you have to find out the magnitude of mu, same thing, of electron in hydrogen atom, again, same system, but this time it is in D state. Earlier it was in S state, right? This time it is in D state. And I am writing the options here. Tell me which option is correct, okay? It's easy now. We solved just very same problem. Now you have to just change a few things and you will get the answer. Okay. Meanwhile, I'll drink some water.
Okay, sir. Sir, answer is,
Which option?
sir, C, sir. Mu B root 6.
Yeah, correct. Good, good. So this means you have understood it completely. So this is the
Yes, sir.
formula, right? So
Yes, sir.
here L you must have taken 2. So your mu will become mu b times under root 2 and 2 plus 1 which is 3. So this is mu b under root 6. Okay,
Okay,
good.
sir.
So then this question is clear to you.
Yes, sir.
Yeah, okay. You will find similar problems in your assignment as well, and you will be
Okay.
easily able to do these questions. Okay.
Okay, sir.
Okay. Let's solve one more, which is similar but slightly different. Okay, similar to this one but slightly different. So we are given d orbital electron again, and we are asked to calculate the possible values of total angular momentum for d electron. Okay, again d electron in one electron state is like hydrogen atom. Okay, so question can be even in hydrogen atom. You just have single electron. So okay, so what does question ask us to calculate? Total angular momentum. What is total
Total.
angular momentum? Total will be orbital plus spin, both, right? So we have to
Yes,
add
sir.
both. In the last question, we were calculating only orbital component, correct?
Yes, sir.
This time, we also have to add spin to it and then see how our answer will change. Okay,
Yes, sir.
so
Somewhat tough, sir.
so instead of L, this time we will take J. This is the total angular
Yes.
momentum, right? And this value, this goes from L plus S all the way up to L minus S. That is correct. So here, what is the value of L? D electron. So L
Yes, sir.
is 2,
Yes, sir. Okay, sir.
and S will be half, right? Because it is an electron, so spin is half. So then J will have what values? So J will have 2 plus half and 2 minus half. These two values. This will be 5 by 2 and this will be 3 by 2. Okay, these two values. Now, so this is the quantum number J, right? This is the quantum number. And what we are asked to
Nice.
calculate? We are asked to calculate the
Total.
possible value of total angular
Ah,
momentum, which will
total.
mean the magnitude. And we know how to find the magnitude. So instead of L, this
Yes.
time we have J. So what will be the value? Under root J times J plus 1. Just like earlier. Instead of L,
Oh,
now
okay.
we have J.
Right. Okay,
Correct?
sir.
And one H cut here. Just the same thing, right?
Okay, sir.
So this will have two values, right? One corresponding to J as 5 by 2 and one corresponding to J as 3 by 2. So we have to solve for both.
Three by.
Okay. So let's write J1. Okay. So which will be the answer? Which option is correct?
That is the first one, sir.
First one. Yeah, good.
Yes, sir.
Okay. So you see the difference. Earlier we were just calculating the orbital motion. Now
Yes,
for
sir.
total motion, we add spin. Okay, and then we find the quantum number j, and magnitude we find in the same way. So instead of L, now
Yes,
we
sir.
have j. Everything remains
Yes, sir.
same. So this is the
Yes, sir.
total angular
Okay.
momentum.
Okay.
Okay,
Yes.
good. Then any doubts?
No, sir. It's clear, sir.
Okay, okay. Let's solve. Then let's solve next question. Okay. So before I solve this one, do you have any other doubts which you want to discuss?
No doubt, sir. Everything's very clear, sir.
Okay.
I understood, sir. Easily, I
Okay.
understood, sir.
Okay. Chalo. Thank you.
Mm.
So I'll write the next one. Let's solve this one. Okay. So may I ask you what degree are you pursuing right now?
I'm working as a professor, sir.
Oh, you are a
Hello, sir.
professor.
Yes, sir. Yes, sir.
Uh, yeah. Which college, sir?
I'm taking engineering physics, sir, but I'm not teaching this subject. I'm
Uh,
interested to join this one, sir.
okay. No, it is good,
Oh,
sir,
but
that you are learning even after becoming a professor. It is a
yes, sir, yes,
very
sir.
good thing. Really admire it.
Yes, sir.
So, sir, have
Um,
you ever seen X-ray diffraction, or have you performed any X-ray diffraction experiment?
yes, sir.
Hmm?
Hello,
Have you
sir. Yes,
uh,
sir.
you have performed this X-ray diffraction experiments in the lab?
Yes, sir. I saw, sir.
You have seen them?
Yes, sir. I see, sir.
Okay. So there, what we do is we have these. So this question that we are solving, this is related. This is very related to the experimental setup. So generally in the labs, we have the
Mm-hmm.
copper source, right? Uh,
Okay, sir.
and then this copper source transmits the X-rays. So the X-rays which we use in the labs, they come from copper, and the
Mm-hmm.
characteristic X-ray is the K alpha line. Okay, so we have one copper target, and then we hit it with some electrons, which produces X-rays, and the characteristic X-rays is called K alpha line. Okay, so first let me write the options, then I'll explain the question.
Okay, sir.
Okay, so this is the question. Okay, now let's try to understand it. So they are talking about characteristic X-ray. Okay, because it is characteristic X-ray, so it will depend on the material which we are choosing. Here our material is copper target.
Cool.
Okay, and the characteristic, it has a special line, this is called K alpha line. Okay, and now we have to
Mm-hmm.
calculate the value of K alpha line. So let me first explain how do you generate X-rays in the lab. Let's say this is let's say our copper target. Okay. Now what we do is we want to hit this copper target with electrons. Okay. So we accelerate these electrons. So we set up some potential. This is let's say plus V. This is minus V. Okay. So then these electrons they get accelerated, right? They gain some energy, EV, right? They gain some energy, EV, and then what happens is they will go and they will hit this target. Okay, like this here. So when they are hitting this target, what will happen? They will remove the electrons from the copper shells.
Got it.
Okay, let's say if this is your nucleus of copper atom, and these are your inner orbitals. Okay, n is equals to 1, 2, so on. So if this is your n is equals to 1 orbital, this electron will come and strike it, and this electron will go out. So now you have a vacancy here, right? So your
Yes.
electron, what from higher levels that can jump to these lower levels, right? And when this transition happens, so when this transition happens, you get an X-ray. Okay?
Yes, sir.
So this is how X-rays are generated.
Yes, sir.
Okay, so this was clear. Now you can
Clear,
see
sir.
because this is copper atom, so this will have some its characteristic wavelength, right? Because this energy difference will depend on this copper atom. If you take some other atom, let's say iron, that wavelength will be different. Therefore, it is called characteristic X-ray wavelength. Okay, because it is the characteristic of the material. Now for K alpha, okay. So for this K alpha, the transition happens from n is equals to 2 to n is equals to 1, which is what we have shown here, right? So the electron will jump
Okay, sir.
from n is equals to 2 to n is equals to 1.
One. Yes.
And now if we remember the Rydberg's formula gives us the wavelength. And the wavelength is then written as 1 by lambda times r times, here let's write z effective, 1 over n1 squared minus 1 over n2 squared. So this is the Rydberg's formula. Now, if you look at the question, they have asked us to assume Moseley's law and assume that our sigma is 1. So from Moseley's law, what we get is, we get that Z effective, we can write as Z minus sigma, where this sigma is the screening constant. Okay, this
Yes,
was
sir. Yes, sir.
discussed in earlier classes, I think in week 2, and this is given to be 1. So this will become Z minus 1. Okay, and
And,
for copper, Z is 29. So this is its atomic number.
yes, sir. Yes, sir.
Okay. So then Z effective will become 28.
Okay.
And then we are already given the value of R, right? We are given the value of
Yes, sir.
R.
Given
Uh,
1.5 given.
yes. Let's put in all the values. Okay. So this is,
Yes.
now we have to just solve this equation and we will get lambda. Okay. So let's write this 1 over lambda
3 by 4.
1.097.
3 by 4 comes. So the right.
This will come 1 minus 1 over 4.
3 by 4, sir.
3 by 4, right? Okay, let me write this as
Yes, sir.
3 by 4. And this 4 will cancel out 28. This will give you 7.
Yes, sir.
So then lambda will be, I can write this as 1 over 1.097 into 7 times 3 is 21 and 10 to the power minus 7. Sorry, plus 7. Like this. Okay.
Okay, sir.
So if you again use the calculator and solve this, so this will become 0.00155, and this 10 to the power 7, when we take it above, this becomes minus 7.
-10.
And then if we want to write it in terms of angstroms, we can write this as 1.55
1.55. Yes,
into
sir.
10 to the power minus 10, which is
Yes.
1.55
So,
angstroms. This was meters
thanks,
and
sir.
this is angstroms. So let's check. There is one option which is matching. So we can say that this is our correct answer, which is option number C. Okay. So is this clear? I think your voice is not coming. Okay, anyway, I'll write the next question. Hmm. Okay, so this is a very long question. Okay, let's read the statements first. So, statement 1 says if the accelerating potential in an X ray tube is increased, the wavelengths of the characteristic X rays do not change. So, is this statement true or not? Okay, so let us draw the setup here. Let's say this is our target. Let's say this is our target material, and here we have electrons which are being accelerated in a potential V. So we have some potential difference V, which gives kinetic energy to these electrons given by EV, and then they go and then they hit the target, right? So what happens is when they hit the target, if this is our atom, they can remove one electron. Okay, so this electron coming here, they can just hit and remove this electron. So we have a vacancy here. So the electrons from higher orbit can transition here, and this will produce X-ray. Okay? So let's say this is N1, this is N2. So we know that the energy of electrons in N1 will depend on only on N1, and the energy in N2 that will depend only on N2. So if we take the difference, and this gives us h nu, this gives us h nu. So what happens is the so we are asked wavelengths. So this lambda we can write as hc over en1 minus en2. Okay, we can write like this, and therefore you can see that it lambda is independent of v. Lambda is independent of v. Okay, so statement 1 is that if the accelerating potential, this is v, right, this is v, if the accelerating potential v in an X-ray tube is increased, the wavelengths of the characteristic X-rays do not change. So this statement is true, correct? This statement is true because it we have already shown that it does not depend on v. Okay? So what we can say is we can say that wavelengths of characteristic X-rays are characteristic of the target material since they depend only on the energy level of the atoms in the target material, right? Therefore, their wavelengths do not change when the accelerating voltage is increased. So, statement 1 is true. Now, let's come to statement 2. So, statement 2 says that when an electron beam strikes the target in an X ray tube, part of the kinetic energy is converted to X ray energy. This is also true, right? This is also true. Right? But is this the correct explanation of one? No, right? This is not the correct explanation. So our answer will be B. Why it is not the correct explanation? Because the characteristic X-rays originate because of electronic transition between discrete energy levels. Right? As we have seen here, the the characteristic X-rays, as we have seen here, they originate because of electronic transition between the discrete energy levels in an atom, and therefore statement 2 is just a general statement regarding the process of X-ray generation. It is a general statement, therefore it is true, but it does not explain why the characteristic X-rays do not change their wavelength if we increase the accelerating potential. Okay, so statement 2 is not the reason. So statement 2 is not the reason why statement 1 is true. Okay, therefore statement 2 is true, but it is not the correct explanation. Okay, so therefore correct option is B. Okay, so let's then, in that case, let's solve one more problem. This will be question 12. Okay? So we are given a titanium atom and we are given its ground state electronic configuration. And the question is that which state is not the possible configuration for titanium. Okay? And these are the options. These are the options. Okay. So first of all, what is this way of writing? So this way of writing means that we fill all the electrons, like the electrons in argon atom, and then in the outermost shell, which will be your n is equals to 4 and 3d, we fill the electrons like this. Okay? So if I draw this titanium, what you will find is that if this is your nucleus, let's draw n is equals to 1, 2, 3. Okay, so you'll have 2 electrons here, right? So this is n is equals to 1, and then 8 in the next one. So 2s2 and 2p6. Then again 8 in this one, n is equals to 3. Okay, and this forms your, so this is your argon. Okay, now you will have your n is equals to 4, and in n is equals to 4 you will have 2 electrons, so this is your 4s2, but also in the D1, so 3D, you will have 2 electrons. So this is your 3D2. Okay. So if we write the electronic configuration of titanium, so titanium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, and then 4s2. Now, this is, I think, called the off-bow principle, where this fourth level electrons are filled before the 3D level. Okay. So one way to realize this is we can write like this: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and then we can make arrows like this. So this is how we fill them, right? So you can see that after filling 3p, we fill 4s first, and then we fill 3d. Yeah? So therefore, it will have electronic configuration like this. Now, what does the question ask? Question asks us that which state is not possible configuration. Now, what is this notation? So this is our general notation, which is L, and then you have the multiplicity here 2s plus 1, and here we have J. So first, what we need to do is find out the possible values of L, S, and J. Okay. So the outermost electrons are the one which is located in this 3D, right? The outermost, this is the unfilled, these are the unfilled electrons. Okay. So we have D2 electrons. Okay. So now this is a two electron system. This is a two electron system. So for both of them, they are d electrons. So L1 and L2 is 2 for both of them. Correct. And now if we use LS coupling, LS coupling, so on adding the total value of L, they can go from L1 plus L2 all the way up to L1 minus L2. So it can go from all the way from 4 to 0. So which imply L can be 0, 1, 2, 3, 4. Correct? So we have 4 different values of L. And what will be S? So S1 is 1 by 2 and S2 is 1 by 2. So S can be 0 or 1. Right? Both of them can have upspin and both of them can have downspin. So total S can be 0 or 1. Okay? So now if S is 0 and L is 4, this gives us J as 4. So the configuration becomes, this will become, so this is 2s plus 1, right? 2s plus 1 is 1. Okay. So the configuration becomes 1 and L is equal to 4 is G and J is equal to 4 is 4, like this. If S is 0 and L is 2, then we have J is 2. Okay. So then the configuration becomes, this is again 1, L is equals to 2 means D, and this becomes 2. If S is 0 and L is 0, so then J is also 0. So this becomes 1S0. Okay. If S is equals to 1 and L is equals to 3, so then your J can have any value from 4, 3 to. So we will have, because now 3 is the multiplicity, so this will have 3, 4, 3, 2. Again, when L is 1, J can have 2, 1, 0, and we can have 3, sorry, this will be P, and 2, 1, 0. Okay, so these are the, let me highlight them in blue. So these are the possible spectroscopic terms for the D2 electrons. Let's check our options. Okay, so 1F3, 1F3 is not here, right? So therefore this is, so we are asked not a possible configuration, so therefore this is incorrect. Let's check the other ones. 1S0, yeah, we have 1S0. 1D2, yes, we have 1D2. 3P0, yes, we have 3P0. Therefore A is the correct option because this is not a possible configuration. Okay, so let's solve one last problem. Okay, so we are given the LS coupling scheme and we are asked that the terms arising from two non-equivalent p electrons are. So we are asked the possible uh, terms that will arise from two non-equivalent p electrons. Okay, so let's solve this one for pp configuration. S1 is equals to half, S2 is equals to half. This means S will be 0 or 1. Okay, L1 is 1, L2 is also 1, so L will be 0, 1 or 2, right? Because L1 plus L2 is 2 and L1 minus L2 is 0. So 0, 1, 2. So when S is 0 and L is 0, this would imply J is 0. So we get 1S0, right? Or 1S. When S is 0 and L is 1, we get J as 1. So this becomes 1P1 or 1P. Now S is 0, L is 2, J is 2. So this becomes 1D2 or 1D. Okay, we are doing good. Now when S is 1, and L is 0, so our J is 1. Okay, so this becomes 3S1, right? Or simply writing as 3S. Now when S is 1 and L is 1, so our J can be 0, 1, 2. Okay, so then we will have 3P 0, 1, 2, or we can also write it as 3P. When your S is 1 and L is 2, so our J can be 1, 2, 3. Okay. So this becomes then 3D, 1, 2, 3, or we can simply write it as 3D. Okay. Thus, spectroscopic terms are 1S, 3S, 1P, 3P, 1D, and 3D, which is option D. Okay. So these are all the problems for today. So in the last we solved two problems based on LS coupling scheme for multi-electron atoms. So this was discussed in this week's lecture. So one thing which we should keep in mind when we are solving these LS coupling problems, which is the LS scheme, we should keep in mind is that when you have heavier atoms, then we do not use LS scheme, but then we use the JJ scheme. So here in the example, we had titanium, which is not a heavy element. So then we can use the LS scheme. So to use the LS scheme, it is very simple. For both the electrons, write down the values of L1, L2 and S1, S2. Find out the total value of L and S, and then take all the cases, right? That when S is S and L has all these values, when S is 1 and L has all these values, and you can get total spectroscopic terms. So here in this case, this was a DD system. So you had two D electrons. In the next problem, we had two P electrons, okay, for TP configuration. So here again, we just take total S value as S1 plus S2, and we get the total S value here. right? And then similarly we get the total L value here, and then we take all the possible cases. So when S is 0 are all the values of L, when S is 1 and then all the values of L. Okay, and then we can simply write these notations. So 1 is 0, 1p1, 1 2, 1d2, and then 3s1, 3p, and 3d. So because this 3 is the multiplicity, therefore you are seeing that, okay, this 3 is the multiplicity, therefore you are seeing that we are getting 3 possible values of j. Therefore it is called multiplicity. Here again we see that multiplicity is 3 and we are getting 3 possible values of j. But this rule is not there in s orbital, right? When your j is 1, then sorry, when your L is 0, then we get only one value irrespective of the multiplicity. Okay, so I hope that clears some of the doubts that you guys have. If you still have any other doubts, you can ask them on the forums, and I will make sure to check the forums and then get back to you with the answers. Again, let me write my email ID in the end. You can email me if you have any doubts, or if you want any discussion on anything, I will try to reply. Okay, so this is my email ID, and yeah, thanks for watching. I'll end the session now.